Of all the different views of the ontology of time, the least popular is the shrinking block. If it comes up at all in a paper or book on the philosophy of time, it may be mentioned in a footnote only to acknowledge all of the logical possibilities, but it's not seriously considered. That's a shame, because the shrinking block is like a criminal who hides in plain sight, never drawing the attention of the detectives trying to solve the case. If we consider it in light of the evidence, we'll see that it's the only one that matches three key, but seemingly incompatible, clues to the nature of reality. Our first clue is the flowing present. The experience of time as a flow of present moments is such a basic aspect of our experience that it's hard to accept there's not an objective basis for it. Then there's the relativity of simultaneity. Special relativity showed that simultaneity is relative to the frame of the observer. This led to a view that relativity requires an eternalist perspective of time, where past, present, and future events are all equally real. And finally, uncertainty. Uncertainty here is not about free will or the lack of it, but the uncertainty that lies at the heart of physical reality according to quantum mechanics, which describes a world where objects don't have definite properties until they are measured, and where a measurement in one location can instantly affect reality in another. Each of these clues represents a fundamental truth about reality, and together they represent a challenge. Even if they may seem to contradict each other, the correct ontology of time should be consistent with all three. So let's start our investigation by briefly calling the usual suspects back in for questioning. Imagine that your flat two-dimensional screen is a stand-in for 4 dimensions of space-time. Time is the vertical dimension, and the blue horizontal line represents all of three-dimensional space at a particular moment in time. The white dots represent events, the things happening in space at that moment in time. According to presentism, only the present is real. No past or future events exist. As the present slice moves continually into the future, the contents of the present are constantly changing. This view aligns well with our experience of time as a flowing present. But the past and future are different, aren't they? We think of the past as fixed and unchanging, and the future as open. So maybe time is really like a growing block. The past and present are real, but no future events exist. The lines here are world lines, representing the path of an object through space-time from its origin in the past to the present moment, and the present is simply the latest slice to be added to the leading edge of the block as it grows. Whatever the relative merits of presentism and the growing block, the special theory of relativity seems to indicate that they both are wrong. Einstein showed that simultaneity is not absolute, but relative to the inertial frame of the observer. Only the speed of light is absolute. An observer moving in one direction at a certain speed would determine, after the fact when the light from the events reached them, that one set of events occurred simultaneously. An observer moving in a different direction would say the same thing about a different space-time slice. Because of this, what is in the present according to one observer may be in the past or the future for another, and no one frame of reference is more valid than any other. The conclusion that is generally drawn is that space-time is like a block, where past, present, and future events are all equally real. In this view, our experience of a flowing present is ultimately an illusion. If we're not willing to give up on an objective reality to a flowing present, we might be drawn to the moving spotlight theory as an alternative to eternalism. In this view, spacetime is still a block, but there is some undefined mechanism that highlights the present, like a spotlight that sweeps over the world lines of spacetime from the past to the future. But both eternalism and the moving spotlight are at odds with uncertainty. They paint a picture of a reality in which things are fixed and definite. Even in the moving spotlight view, the properties of an object at a particular location in spacetime are just waiting there to be illuminated, while quantum mechanics tells us that an object has no definite properties until it is measured, when it suddenly snaps out of its superposed state. Since we want our theory to match all three clues, we'll move on and look at our final and most unlikely suspect. At first glance, the shrinking block only seems to check one of our three boxes. As the block shrinks, the present disappears into the trailing edge. This gives us a mechanism to explain why the present is unique and why time seems to flow. But how can the shrinking block account for uncertainty and for the relativity of simultaneity? Let's start with uncertainty. To show that the shrinking block is compatible with uncertainty, we first have to look closer at what happens to events when they fall into the trailing edge of the block? Do they really disappear altogether? This question is reminiscent of the famous black hole information paradox, which led to the idea of the holographic principle in physics. In the context of a black hole, the holographic principle says that the information needed to describe objects that fall into a black hole becomes encoded in fluctuations on the surface of the event horizon. So let's apply the holographic principle to the shrinking block and say that the answer is the same. No. When an event hits the trailing edge of the shrinking block, it does not really disappear. Instead, it is translated or encoded into a pattern of information spread across the surface of the trailing edge, and so on when the next set of events falls into the trailing edge and the set after that. In other words, the trailing edge contains a hologram of the past. Now let's take the case of an entangled pair of particles, B and C, which emerge from a single source particle A traveling in opposite directions. These particles have an attribute, represented here by their color, which is subject to Bell's theorem. So because they are entangled, what we see here can't be the whole story. In some sense, B and C can't have a definite color until one of them is measured. But of course our observations are really observations of the past. So we should look at how these two particles are encoded on the trailing edge to understand how uncertainty enters the equation. Particles B and C could be encoded as two separate objects, each with a color. We'll symbolize that possibility with these two circles, while keeping in mind that the patterns on the surface of the hologram wouldn't actually be localized in this way. In this case, there is no uncertainty about what the outcome of an observation would be. Or the entangled particles could be encoded together, so that the colors are associated with the pair of particles as a system. If they are encoded together, then we see that an observation forces a choice, and that the choice of which color corresponds to which particle is determined for both particles simultaneously. But it can go either way. This is a model for how the shrinking block can account for quantum uncertainty and the results of the experimental test of Bell's theorem. It's like looking at a hologram containing multiple views of the same object, but you can only see one aspect or the other, not both simultaneously. The idea that the trailing edge of the shrinking block contains a complete hologram of the past also puts a new spin on the relativity of simultaneity. Here we have observer A and observer B moving through spacetime in different inertial frames. Each observer would view a particular three-dimensional slice of the past based on their inertial frame, and so they are looking at the same hologram from different angles. And since the angles are different, each would be able to pick out different sets of events which they would judge to be at equal distance, and which they would therefore conclude occurred simultaneously. Observer A would determine that events C and D happened simultaneously. B would see a different slice of the same past and would conclude that no, C and E occurred at the same time. In this way, the shrinking block can satisfy the requirement of being able to foliate spacetime as needed based on the reference frame of the observer. So that's the case for the shrinking block, or at least a rough outline for the opening argument. Of course, a really compelling case would require much more detail and rigor, but hopefully this presentation establishes that it's a case worth making.